Next, now we are ready to do the insertion sort. 8.2, implementation of insertion sort. Yeah. That will be pretty easy. Yeah, we just complete it. Okay, all right. Let us estimate efficiency. Yeah. When we complete the whole sorting process, at the same time, we estimate efficiency. Yeah. Compare and shift operation. Yeah. So that's what we do in a typical operation like this. Okay, all right. Worst case efficiency. Yeah. When you do from the first to the last one, yeah. One element you do nothing, but two elements you need to do one comparison. Three elements you need to do two comparisons, and so on. Okay? The last element you need to do n-1 comparisons. Yeah. So then for the worst case efficiency, you have this expression. Okay. That is big theta of n squared. Worst case. How about the best case? Okay. The best case efficiency, every time when you insert a new element, you only do one comparison. That means you have the best case for the insertion operation from the beginning to the end. I need to drink some water. From beginning to end. So you have n-1 comparison. Then the best case efficiency, big theta of n. Compare these two cases. Worst case, big theta of n squared, best case, big theta of n. How different they are. How different they are. Because if you recall, selection sort and the bubble sort, excuse me. For best case, worst case, both you have big theta of n squared, right? Same. But here, quite different. N squared versus n. That's a big property for insertion sort. Yeah. Each sort has some special property. So this is a nice property for the insertion sort. Can we take advantage of this property? Yes, because this property is so special, we should take advantage of it. Okay, yes. In the real world applications, if you encounter some appropriate situations where you can apply insertion sort, you can take advantage of its fast best case efficiency. Let me give you a special case. All right. Yeah, average case. Yeah, we can find it. All right. Yeah. Here I do not do the detail work. Yeah, but it should not be very hard to find big theta of n squared for the average case. Yeah, but I like to show you a special use case for this insertion sort as a conclusion. Okay, all right. If the given array is almost sorted in the real world situation, do you have sometimes you may have this kind of situation? The data is almost sorted. It is not sorted, but almost sorted. Only in some small isolated places, the data is not sorted. You just fix that unsorted part. Yeah. In that situation, the insertion sort is the best. Yeah. So look at the data. Let me describe the data using this line segment. Okay, yeah. Then in these isolated locations, the data not in order. We need to fix these scattered, isolated places. In this situation, the best way to do it, we applied insertion sort, so we can take advantage of its super fast, best case efficiency. Super fast, best case efficiency. All right, yeah. So try to, pick up this interesting property. Yeah. Probably sometime it's useful in the real world situation. Yeah. Because the reason is, if you apply any other sorting algorithms, later we will learn a few more sorting algorithms. You will see no other algorithm will do as well as insertion sort on this special case. This special case, insertion sort is the best. Okay. All right. Yeah. So at this point, we complete the whole insertion sort. It's pretty short.